we're going to introduce reinforcement learning, and reinforcement learning is a broad field by itself, and I'm going to highlight the building blocks, that how it relates to the stuff that we've learned, and how can we use the stuff we've learned within the context of reinforcement learning. So clearly we've been talking about learning in neural networks in general and deep learning, and we've been focusing primarily on supervised learning, which is you're giving the full data and the corresponding, so the training data, for example, evaluation data, validation data, and you need an input and an output or a pair. Sometimes the output, we call it a label or a target, and that's how supervised learning works. And the working horse for supervised learning would be a family of the gradient descent, so variations of gradient descent. And the reason that people settled on that, because it's simple, straightforward, and it does the job. So you could add some other nuances to it to improve things, but so far people have found that sticking with the gradient descent family has been very profitable or positive. Unsupervised learning, we just touched a little bit about it onto this area. When we looked at forms of PCA, we focused primarily on the algebraic method of PCA. There is a corresponding adaptive PCA, and the adaptive PCA is like the PCA, obviously, is cast as a linear map, and it's a single layer representation of neural network, and the adaptive will be to determine the vectors or the weights adaptively from the data, and hopefully if it is converging to a PCA representation, then those weights become the rows of the weight matrix, become eigenvectors of the covariance of the data. The extension of PCA is now referred to as auto-encoders. You don't have to stick to one layer. You can have multiplicity of layers. You can have a deep layer. We'll talk about that. And another form of unsupervised learning also is ICA, Independent Component Analysis. We briefly touched on that concept, and we learned about the sparsity and independent components, and how that could be simplified by an exponential probability density, which corresponds to an L1 norm in the algebraic form. What we're going to focus on in this reinforcement learning is clearly slightly different in many ways. One way is the reinforcement learning relates to control as opposed to just sensing. So what we've talked about so far is that we're sensing some data and we're trying to estimate a mapping for input-output data. This one is trying to introduce an action on the environment or the system. That's one. Secondly, it's going to follow a probing technique where we say it interacts with the environment, and based on the response of that environment, evaluation of that response, it makes a decision about improving its next action. So there's a word or terminology that says actor, which modifies or improves actions. We also talk online or sequential or incremental improvement resulting on the result or the evaluation or the response from the environment. So this is a summary that I thought of, which summarizes the upper diagram represents all the stuff we've been looking at, which really, in a systems level, you are trying to create an estimator. So you have sensory input data, you have a target or a label, and you have some magic red block that actually can map the input to that label or the target perfectly. And we don't know that magic map, or we call it observer here. It could be by human facilities, could be by some magic things based on the data. So the idea for our purposes, we create a block, which we call it the net, and we have access to the input and the target on this end, and we can use this data to modify this net. The structure of the net, as we already know, could be convnet, could be recurrent neural network. It has parameters, and this technique, it extracts discrepancy between the target and the output here, I say discrepancy, I don't want to say difference, because difference is one form of it, because it depends on the loss function you use, the optimizer that we all know. And the goal is to change those parameters or weights over an epoch. So you have the whole data available to you, and you just run the data epoch by epoch to incrementally change the weights. The end result, you're going to achieve a mapping from an input to an output, and this output is going to be approximating or reproducing something close to the target. So this is in the domain of creating an estimator or an observer, depending on the field. Reinforcement learning is slightly different in the sense that now your network, which is here, is actually generate an action on the environment. It's a control. It's like a robot, or you're driving a vehicle, you create some action, and then the environment or the system or the robot or the car gives you some data, which we refer to it here as measurement or the state. And we say the state because the state presumably captures all the information and knowledge about the dynamics of this environment. And based on the state, you create something that assesses the value of that response. We call it a value measure or value metric. And then based on that value metric, you change your strategy or rules or policy or function in order for you to generate a better action. So it is in the domain of control and human controller aspect. So there's an action and measurements, and you improve the action incrementally over time. So conceptually, there are two different frames. So if we focus on this thing, what are the applications for this reinforcement learning? We know that one big application has been creating games. So when you look at games, there's some action. You have a player, and the player will make a decision and have an action. That's one application. Another application, self-driving vehicles. So you have a robot or a system inside that makes a decision about the steering or the pedal, and that's an action, and based on the measurements of the response, it responds. So point is, these are two huge domains of applications that reinforcement learning has been shining and been the leading in that aspect. And the reason is, reinforcement learning, you generate a control. The stuff that we've been talking about so far, we don't generate control. We just need to estimate a relationship between an input data and an output data of some sort. And the classification, detection, and prediction all fall into these categories. So if we begin to motivate this process of reinforcement learning, we have a simple cartoon problem. You have squares here, and you have a starting point box, and you have an ending box. And imagine you have a mouse that starts at the starting point. It wants to go to the end point. And for example, the mouse could be limited to moving, in this case we say down and right, just to make the problem tractable. And every time it crosses one of these lines, there's a cost. So what I'm saying here, I put the cost. If it crosses this line, there's a cost of -3. If there's no number here, that means the cost is -1. And the idea is that what path should this mouse take that minimizes the total cost? So if you look at it here, typically you can either look locally in one step cost, or your goal is to make sure the total cost of the whole path to the end would be the minimum. So I'm hiding something here from you. And if you look at it, you have option one is to look locally, only one step. But if you look one step between this side and this side, this is -1, this is -3. Obviously, you go with -1. And then when you come to this side, you say -2 and -2. It doesn't matter. You can go either way. But if you focus on the initial steps, obviously, it's better for you to choose this direction. Okay? But that may not be the case for the total cost. And reason being is that it turns out that if you go this way and this way, that will be the least cost for you, even though initially you may be paying more cost. And that makes sense, because in life we don't just look at one step, we look at several steps ahead. Now, dynamic programming from optimal control came up with a solution for this to create a strategy. And the strategy says if you want to have the minimum path, you better start from the end first and traverse backward. You do two things when you do that. One, you're going to examine less paths. That's one. Okay, so if you go forward, you have more exponential growth of paths. And if you want to check all the paths, they're going to be exponentially growing. If you start from the end and go backward, there's some paths you're just going to drop. You're not going to consider. Only consider potential candidates for minimum total gain or cost. So one result from dynamic programming and optimization, optimal control, is that you start from the end. The other result is that you have the optimal solution, but you have to solve it offline. If you do the optimal solution, which is analytically proven to be the optimal, you end up with a strategy that you have to implement offline, and then you have the optimal path and optimal control strategy and you do it. Obviously, this is not practical in the real world. So what reinforcement learning is trying to do, so clearly what we've done here is that if I traverse things backward in time, I discover that the minimum path is really this path that I have for you here, because that will be the total cost will be the least among all the other paths. That's point one. Point two, you have other paths that may stop at some point, like this path is optimal up to this point, but it can't go anymore because if you have other options which are less expensive for you. So you have many different paths, but the optimal path from this point will be this unique path in this particular case. So that's from optimal control and optimization. We've known this for some time. What reinforcement learning is going to do is going to relax these analytical conditions. Its goal is to have forward. It doesn't have to do things backward in time. You want to have the computation or the learning forward in time by probing techniques, one step at a time. And also, it doesn't require it to be theoretically optimal. It could be approximately optimal or close to an optimal. And the other thing is going to combine optimality with adaptivity. So you're also going to adaptively converge to that optimal solution. It's not going to be getting the full optimal, but it's going to be approximate enough for your particular application. So, the words that I'm throwing in here that are often used in reinforcement learning are the word actor or agent that generates initial control policy. And when we use the word policies, we are looking at the rules that you follow or the function that you're going to follow, not the actual control signal that you're going to probe. So for example, if I'm driving my vehicle, the rules will be the strategy of which turn how I'm going to turn, how much the turn is, and all that stuff, instead of the actual one turn in one instant. And it uses the probing technique, meaning that you're going to supply a guess control, and you look at the response, and if the response is poorly, you're going to correct the next time you go about it, which is things that we all do in driving. You try turn the car, and if it's too much, you correct for it, and things of that sort. So you have it incrementally, one step at a time. The words also value or cost or reward is associated to help you evaluate the initial control or policy or actor that you generate. As I mentioned to you earlier, there are many approaches that come from different fields to reinforcement learning. We're going to focus here on one class or subclass of these approaches referred to as the Actor-Critic structure. And the reason we are going to focus on this structure because it has some analytical support. It has some analysis, and people were able to pin down that this thing indeed converges, and guaranteed some converges in many cases, to a near optimal solution. The steps of the process, this is going to be a discrete instant by instant process, and we focus for every action, we focus on two steps. One, you have a policy evaluation by the critic. So in other words, you try some action, you get a response, hopefully you get the core of that response, which we refer to as the state, and then you're going to evaluate, based on that state, you're going to evaluate that response, and that response tells you the action that you did, the policy that you have is good or bad or some in between. And then the next thing, you use that information to improve the next policy or the next actions that you have. So typically the drawing that I have, this is our system, our environment, our vehicle, our robot, our game basically, and this is the agent that interacts with this system. To put this one on firm perspectives, we have to have formal definitions, and we use things from classical control, yet we're going to show at what point we're going to deviate from that to enable us to do two things. One, to solve the optimal control forward in time, at one step at a time. And two, we're not going to insist on having the full optimal, but we have things that converge to an optimal. So we can label the state in one-step state or instant at instant I, arbitrary instant I. We have discrete system I'm showing you here. And so I is the dummy index, and U sub I is the action or the agent controlled at instant I. And we have something called reward or utility for one step. So if the state is xi and the control action of this I instant given to me like this, I have something that says in one step, that's the reward or the function or the loss or the cost that we're going to have. Also referred to sometimes as utility. And I have to throw all these different names because you see all these different names interchangeably depending on what references you're reading. And so let me just do it safely here. So the concept of discounted overall cost to go from the present instant. So I am at the present instant K. Okay? I want to look at the so-called cost to go, which is from this point forward, assuming I'm going forward to infinity in the general case. And the concept of discounted overall cost says if you give me the reward for one step, I'm going to discount that over time by having a gamma which is less than 1, near 1, but then it has the power, so as you go further in the steps, this will be discounted further. And this will be the total cost along the whole path. The only reason that you have this discounted control is that then that cost will make sense. If not, imagine that this rewards that each step is equal to 1 and you have an infinite path. When you sum it, this will be infinity. So the concept of discounted control just makes sure that the cost that you have is finite and analytical for analytical purposes. And also, it denotes that my focus is more on the immediate step than on later steps. As I go further, right now I'm discounting the cost for the next steps. So I have more focus on the one initial step that I have than on the subsequent steps, even though I'm looking at the subsequent step cost. So this is the expression, the cost to go, or the value, or the expression that you want to make sure you minimize to obtain an optimal policy, an optimal control. Also, you're interested in having a state feedback, meaning that my control will react based on the measurements or the state of the system. It's like when you're driving a vehicle, you look at where the vehicle is going, you react to that based on the state of the system. In other words, this control is going to be some function we don't know yet of that state, initial state. Once we plug this feedback, then we have this expression, and your strategy should minimize this cost. So if you have a cost, our goal is always to minimize it. That's optimality, okay? And this two things here just showing you an expression. When we have minimum, this is where you're going to put a star on this value that when you obtain this minimum of the total cost to go. So far, just basic stuff. Once you optimize the cost, obviously that optimized cost over all possible policies, rules, functions, all these are same terminologies. You have also the optimal policy, which is the optimal feedback control that you're going to apply to achieve minimality. So this is optimal value or cost or loss. This will be the corresponding optimal policy that achieves this minimality. So if we look back at optimal control, we have the concept of dynamic programming, DP. We also have dynamic programming is based on the so-called Delmond's optimality principle. These are all solid analytical techniques. The only drawback is that those techniques have to be done offline to generate the optimal control, not in real time or online. That's the drawback. Secondly, to solve these analytical methods, you have to solve things backward in time. These are two drawbacks that reinforcement learning eliminates. So there are techniques called policy iterations and value iterations. So reinforcement learning examples, we're going to talk about something called temporal differences and approximate dynamic programming as opposed to the pure dynamic programming. So the Delmond's optimality principle and the difference equation. So this is the total cost to go, discounted cost to go. You focus on the present instant k and the next instant k plus 1. And you want to pull out the expression for that, which is the reward for that, from this expression. All you're doing here is just breaking this infinite sum to two terms. One has the reward for one step reward, and then plus gamma, the other stuff, and this other stuff is going to have the same form. So all the manipulations here is just showing you this equation could be written like this equation. Meaning I have a scalar loss function or cost of this current state is going to equal to reward for one step with this strategy for feedback control, and then we have a discount gamma which is less than 1, between 0 and 1, and we have the same, this whole stuff here I put underline here underneath it because this is going to be exactly the same expression we have here, except now you are focusing on k plus 1. So this equation v here is a scalar equals to some reward for one step plus gamma, the scalar at the next k plus 1. This is a scalar difference equation. Okay? Difference equation because I can take this guy to the other side and I have a difference between the value at k and the value at k plus 1. Okay? So let me just jump here and recite for you what Delmond's optimality principle says that led to dynamic programming. The paragraph that you see here is common sense. The interpretation analytically for it is a challenge. But what it says, an optimal policy has the property that no matter what the previous states and decisions have been, the remaining decisions must constitute an optimal policy with regard to the state resulting from those previous decisions. All it says in plain language is that it doesn't matter what brought you to this point. To achieve optimality, you look at where you are at the state and you try to generate optimal policies from this state forward. Meaning that we look at where you are, it doesn't matter what brought you to that particular state. Okay? But if you know where you are, I can devise for you an optimal policy from that point. If you're another point, another state, we can devise an optimal point, a policy forward from that state. So it's really common sense. What this translates to mathematically is that instead of, when you look at the optimality that we have here, the cost, we put everything in parentheses here, and we said we want to find the minimum of this expression over all policies, and if we do, then we put a star on this V on this side. But there's no star on this V inside here. Meaning that you have to explore this expression over all the trajectories, all the policies, to obtain this one. The Bellman's optimality principle, when interpreted analytically, it results in putting a star on this V, meaning that I'm obtaining this optimal, but I already have the optimal expression on the value at k plus 1. Seemingly trivial, but it's very powerful. And what this one does, it suggests for you to begin from the end. Because at the end, you know what the result is. That's your optimal path, and you traverse backward. So this one suggests for you traversing backward one step at a time, one cost at a time, in order for you to trace to the step where the optimal is. So placing this dot here, which means this is an optimal, forces me to begin at the end, which I know it's optimal, moving backward. Okay? So if you do this one step by step, you have this optimal path, and if you come to this point, I have two branches, you have to tell me where you're going to be coming from. If you're coming from this point, I say from this point, here's the optimal path. But let's say you say, no, I'm at this state, then I can have a different optimal path for you. So I can incrementally grow this optimality from the backward in time. And of course, the minute you have the optimal value, you have the optimal policy, which is really what is the function or the rules that you're following to generate these feedback control. So this is a mind twister for many people, because you read this paragraph and it makes sense and it's obvious, and then how this one results in placing a dot, which means optimality for this function. So you're optimizing over more restrictive domains than in this very original case. So everything we've talked about right now really comes from optimal control and dynamic programming. Some of you already been exposed to this in some ways, some haven't. What does reinforcement learning do in this particular type of reinforcement learning? Because you may come across other forms, other structures of reinforcement learning. So in this thing, we're going to forward in time, so the evaluation is going to be forward in time steps, not backward in time. We're going to violate exactly what the dynamic programming is saying. And two, we're not going to insist on having analytically optimal policy or optimal value. And we're going to do this by iterative techniques, and we're using available data, measurements. So we keep measuring and improving our initial guesses. So the Bellman's equation has been noted that this optimal equation is part of a family of equations that are referred to as the fixed point equations. That's a big breakthrough in optimization. What does fixed point equation mean? Have you ever tried to find roots of polynomials? And what you do, and if you have nonlinear polynomial and you want to find the roots, what do? You initialize it. You start, okay, I'm going to initialize something equal to 0, and then you iterate. And when you iterate, you're going to converge to some solutions. That property is a fixed point property of equations. It turns out the Delmond equation that we have here, okay, is part of that family, meaning that, yes, you wanted this optimal equation relation between the right and the left sides, but we don't have to have the optimal h on the outset. We can start from guessing the h, and if we keep iterating, so we plug in the h on this side and we obtain v, and then we plug it again, reiterate, we're going to have a conversion to something close to that. So the property that we're exploiting here is this fixed point equation property. We're going to apply it on this discrete equation. So that results in techniques called, for example, policy iterations or value iteration. The word policy refers to that you're trying to iterate over the control, the variable h we have here, the feedback control. The value iteration refers to over the cost iterations. The word value, same as the word cost in this context, same as the word loss in deep learning, and so on and so forth. So we relax the equation, and if you noted here, we plug in indices like j's, okay, and we start from guess of some rule. So when I start driving my car, I don't know what needs to be done, so I start just moving left and right randomly. So that's my initial guess. Okay, if you have a child driving a vehicle, they may have some wild initial guesses, right? But over time, you'd learn and you improve. So here's my initial guess, h sub 0. You plug it in, and then you do iterations over this one here. And the idea with this iteration, like when you find roots of polynomials in a way, analogy here, you would be improving from one step to the next in minimizing this value. You can have it in the policy, so you can have it, and then once you have this expression, you take this, you plug it in here in this case, and you try to find the local minima, and this best solution that you have over this guess will give you an improved policy, which you iterate again. So you can imagine with this J index, we can iterate, and we will have a better, improved policy. And this is one way of looking at it. You can also have the same equation by having another dummy index I, and notice that I have Vj here, Vj the same, and I can iterate over the same equation with another index. So the whole key point here is we're exploiting this fixed point property. We start from guess and we keep iterating, and we're going to move towards that optimal policy and optimal value. So if you apply it to the value, so again, you do the same thing. You initialize with some policy, and the word policy here is just a terminology that people have used. It means a function, some guess of the strategy or the rules they're going to apply. When I start driving, my rule is going to be just moving this way, for instance. So you could see this is very trivial here in the sense that you have iterations, and then you do one iteration, then you take the min after this one iteration, that gives you a next estimate, and you keep doing this improvement one step at a time. Another concept, another technique called the temporal difference error. So I think this will be maybe more in our line, that you look at the Delmond equation that we have here, which is discrete equation. This v is a variable, it's a scalar variable, function of the state, but this is a scalar equation. All these guys are scalars. And this one is at instant k, this is at k plus 1. This one, equality happens, you're an optimal, but you're going to say, what if this side is not equal to this side? I deviate from it. So I'm going to take this one, this quantity here, put it to the other side, If I put this on the side, that means this is not going to equal to this, is going to have some error, discrepancy. So I created what's called temporal difference error, which means those two sides may not be equal because I have a lousy choice of H. It's not the one that does the job, solves this equation, right? It's like when you have a polynomial, this polynomial should equal to 0, but when you plug in some value that's not root, it's not going to be 0. All right? So you have an error. The other concept is that this H, which is a policy, and this V, which is a value, we don't know what they are. So can we have an approximator, something that could adjust to whatever function that we have? Here comes a neural network model, right? Because a neural network is universal approximator. And in this case, I'm saying, okay, suppose I'm going to estimate this function, value function, scalar function, by a neural network. This is scalar, so it's a single output. In this case, I'm showing you a one layer. We have X, nonlinearity, then weights. But this guy here could actually be an output of a multi-layer neural network. So this whole thing could be represented by any type of network that has parameters. I'm showing you one example here. So if you have the value function which you don't know, and you have a universal approximator neural network that tried to estimate it, and you have parameters, and you have an error, then this is a candidate of using adaptive techniques and neural networks. Because now here's my error, and I plugged in the weights, and I have parameters. So can I have a loss function based on this error of some sort? And I want to minimize this error, make it close to 0. Because when I make this error equal to 0, that means this side equal to this side. Then I'm exactly at the Delmond equation. And I have parameters, and the trick of pushing this error or the loss of the error to 0 is by minimizing this loss that I'm going to create for myself. And I have parameters that keeps adjusting. And the idea, once the parameters adjust to some point, you have a value function which you can evaluate the performance of your system. So I have an error with parameters that need to be minimized using available observations of the environment, state data. So this is really an ingredient for neural network, and you can have it deep neural network, and this is exactly what the group at Google has developed in having capable reinforcement learning techniques that beat the champion, I guess, of the game Go some years ago, and they have a lot of challenging games. Now, I have to clarify one point. There are a lot of different families of reinforcement learning, and we're only discussing one form that has some backup in analysis. There are other forms that may be fully heuristic, and their degree of analytical support for those things here. But you can see the idea that if we have lots of data, which we do in driving vehicles or in games, we can generate this data, and we can do this one by probing. So you try something and it's wrong, you correct it, you move on until you fine-tune your value function and your strategy. So really this is the flavor that I want to stop at this point, because now I showed you the analytical backbone of some of these techniques and how we can relax this optimization technique, but adaptivity, and we don't insist on solving complex equations such as the Riccati equation or what have you, the tradition that is done in optimal control, and we're going to eliminate the offline features of optimality, and we're going to pay the price of not achieving the optimal on the outset, but we converge to this optimal sequentially, incrementally, as we improve over time. And because we have availability of huge data, we're going to exploit that and just keep doing it. And the idea is obviously a mix of analysis and also observation of live things, humans and animals, and how they approach these techniques. And this is the flavor that I want. Further readings, you can go to these references. There are more things about the Q factor, Q learning, TD0, TD lambda, approximate dynamic programming, the Markov chain models, finite state, and control sets. There are a lot of things, and actually Google has developed also a wonderful library that is dedicated to reinforcement learning with a lot of capabilities. Like we have right now TensorFlow, there's a unique library dedicated for reinforcement learning. Any questions? Okay.